Okay, in this video we're going to continue to talk about logs, and we're going to start by some common notation that you need to know when we use logs. And the two most common logs that you take are the common log and the natural log. The common log simply means log with base of 10. That's all that it means. So from here on forward, you'll never, ever see in a textbook or me write log base 10 of, let's say, 5 or something like that. You'll never see that written. If I wanted to write log base 10 of 5, all I need to write is log of 5. Oops, that's not a very good 5, is it? Log of 5. You don't need, if you don't see, so if it looks like, hey, somebody forgot to write the base of the log, it's assumed that it's really it's a 10, but it's just not written there. That's log base 10. It's the common log. So if you don't see a base value for the log, you know it's going to be 10. It's just the common log. On the other hand, there's the natural log. You guys learned in section 8.3 the natural number. That was the number e. So this is just log with base e. So you'll never, ever see this written, log base e of, let's say, 6. Okay, that has its own special notation, just especially to confuse you guys. Log base e of 6 is going to be written like this. And that is confusing because it doesn't even look like a log. The way you actually read this is natural log of 6. That's the natural log of 6. You would think it would be NL6 for natural log 6, but it's not. It's written LN 6. So whenever you see LN, all that means, LN just means log base E. That's all that it means. So a lot of students freak out when they see LN. Just know that it's a log with the base E, and it has its own fancy notation. And it takes a little getting used to. We're going to kind of move on to inverse properties of logs and apply them. If f of x is the exponential function, just b to the x, and let's say g of x is the logarithmic function log base b of x, then if you compose that, meaning if you plug g of x in for f of x, you would get b to the power log base b of x. And something remarkable happens if you were to actually compute that. It's just equal to x. And likewise, if you did the reverse composition, you did g of f of x, and you actually plugged in the exponential function in for x in the log, you would get log base b of b to the x. And that turns out to be x. What that means then is that log functions and exponential functions are inverses. They're opposite operations. Let's actually do some inverse properties with logs then, equipped with those definitions. Now, some students get confused with, but they can be the easiest problems you run into. Just remember, if you have an exponent or an exponential expression, if the base is b and in the exponent is log with the same base, right? The exponent and the logs undo each other as long as the bases are the same, and we just get x. So the reason why I'm bringing that up is because when I look at a, I notice this is like an exponential type of expression. Now you might be saying, well, okay, that's all good and fine, and log is the exponent, but the bases don't match. Here the base is 10, and here the base is not written. Remember what we just discussed. If you don't see the base written, it's assumed it's a 10. So in fact the bases do match, and so the answer to this is just 2.3. That's it. There's really no math to show per se. On the other hand, the other composition we did was if we had the log with base b of b to the power x, we got x. Again, key is the base of the log and the base of the exponent in the log both have to match. Now here in part B, they don't match. 8 is not a 2. So you would be stuck unless you knew how to rewrite 8 so it is a power of 2. And I do know a way of doing that. I can rewrite this as log base 2, and instead of 8 to the x, I can rewrite 8 as 2 cubed. Right? Isn't that the same thing as 8? So instead of 8, I'm writing 2 cubed, which is the same as log base 2 of 2 to the, and we multiply these exponents, right? 2 to the 3x power. Now the bases match, and if I use the inverse property that we have written here, I would just get out that exponent since, oops, I didn't want to write the base of 2, or excuse me, yeah, that is a base 2, okay, I confused myself there and thought that was a 3. The bases just match. I just get the exponent 3x out. And again, there's really not a whole lot of math besides making sure that the bases match before you take that exponent out. The last example, as far as inverses go, that I'm going to show you is how to find the inverse of the function. So for a, we have y equals log base a half of x. From the definition of a logarithm, we know that the inverse function for this is going to be an exponential function. Now, to be honest with you, all we need to really do is switch x and y like we always did, and if we do that, I would get x equals log base 1/2 of y. Now we have to solve for y, right? In last chapter we learned to, if we're finding the inverse, is switch x and y, then solve for y. The way you're going to do that, guys, is by writing this in exponential form. Remember, the log of a number y, in this case, is equal to the exponent x to which the base 1/2 is being raised. So if I wrote this as an exponent, it would be 1/2 as the base, raised to the, I should put that in parentheses, right? Raised to the x power is y. And so we've just figured out the inverse. Right there, there's your inverse function. Y equals 1/2 to the power x. Let's do the next one. Here we have the original function y equals ln of x minus 2. I'm going to switch x and y and get x equals ln of y minus 2. Now what I'm going to do is write it in exponential form. The trick here, guys, is to know what the base of ln is. And if you go back to that very first thing we talked about, there's the natural log. That just means base e. So this is like saying, okay, e, that base e raised to the power x is equal to y minus 2. Right? So the log of the y minus 2 equals the exponent x with that base e. One more step, if we solve for y, we just have to add 2 to both sides, right? And if you do, you get e to the power x plus 2. Now make sure that 2 is not in the exponent, it's just e to the exponent x, and then we add 2. So the inverse of that guy is just e to the x plus 2. Notice how our inverse of a log function is an exponential function. Now, what I would like you to do at this point is maybe take a moment and try to do the following couple problems. It's kind of a little self-quiz. I'm going to give you a little hint on number 5. Remember, this is the common log, and if you forgot what the common log is, go back to the front and you'll know what the base is. If you spend too long on number 5, you're doing it wrong. Look at those inverse properties like f of g of x and g of f of x. This one's also kind of tricky with leaving the base as 81. You want to try to rewrite that base, and that's about all I'm going to say. So rewrite the base, so maybe the base of the log matches the base of the exponent in the log. And then 7 and 8 are kind of just like the inverses we just did. Switch x and y, solve for y by writing in exponential form. Okay, so hopefully you've just given those couple problems a chance to see how well you've understood. The way I'm going to end this video is with how we can use the graphs of logs to solve some real-life problems. And we'll use our graphing calculators to do some of this, so make sure you grab your graphing calculator at this point. In this example, it says the slope S of a beach is related to the average diameter d in millimeters of sand particles on the beach by the following equation. Find the slope of a beach if the average diameter of a sand particle is 0.5 millimeters. So part A is actually kind of easy because they're telling you what d equals. They're saying the diameter of a piece of sand or a grain of sand is 0.5 millimeters. And I think all we have to do to find the slope is plug that in. So it's going to be the slope is 0.159 plus 0.118, and then it's times the log of 0.5. So if you were to use your calculator, you have to make sure you use the common log button, and I think you should see it on your calculator. So what I've done is I've grabbed my graphing calculator and I've typed in the 0.159 plus 0.118 log of 0.5, and if you do hit enter, you'd get the slope of the beach is about 0.12. If we were around just to, usually we go to 2 decimal places, so let's go to 2 decimal places here. So we're going to have a slope of our beach at about 0.12 if we round it. Now for part B, we're going to use our graphing calculator to help see if we can, hold on one second. Okay, if we can use our calculator to help figure out the average diameter of sand particles on the beach if the slope is 0.3. Now here, they're not giving us the diameter, they're giving us the slope is 0.3. And we need to find the diameter. So if we used our formula, it would become 0.3 equals the 0.159 plus 0.118 log of d. Now, that was a terrible d. Let's rewrite that d. So, we don't know how to solve for d, guys. We don't know how to solve a log equation yet, but what I do know is what I taught you last chapter. If I want to solve an equation, I could do it graphically. Let's put in y1 over here as 0.3, and this guy I'm going to let be y2, and I'm going to see where these two curves intersect. And let's grab our graphing calculator and do that right now. So I'm going to go to y equals, and y1 let's let be 0.3. y2 I'm going to type in 0.159 plus 0.118 log of d, which I can't type in a d, so I'm going to type in an x. And before I go ahead and just hit zoom 6, I'm going to go to the window and kind of use my noggin for a second to arrange this. I know that y1, y equals 0.3, is just a horizontal line that's up 0.3 off of the x-axis. So when I go to my window, I'm going to make sure my y max doesn't go much higher than, let's say, just 1. And my y min, I'm going to go from 0 to 1, because again, that y1 is just 0.3. It's a horizontal line. I want to be able to see that. And I might even change my y scale to count by 0.1s. And I know that the x value here that I'm trying to figure out is the diameter of a sand particle. It's impossible for the diameter to be negative. So let's just go from, I don't know, 0 to 10 and see what kind of graph we get here. Let's graph this. Okay, so here we go. I can see y1 is the horizontal line, and y2 is that curve, and I can't quite see where they intersect. So it looks like I have to go further to the right. Let's change our x max to 25. There we go. Now I can see that they intersect. I'm going to hit second, trace, and I'm going to choose intersect, number 5. And remember, just like before, you hit enter 3 times, and I get that the diameter of a particle of sand in millimeters is about 15.66 millimeters. So for this one, oops, didn't want to really do that. For this one, my diameter is about 15 5.66 millimeters. Now, what I want you to try, and I know this might not be written on your worksheet, but I want you to try to use your calculator to graph the model to find the average diameter of sand particles on a beach if the slope is now 0.54. So, again, for y1, you're going to do 0.54, and your y2 is going to be that entire expression, right? Same one that you have, and see if you can use the intersect feature to find out how many millimeters that is, and see if that even makes sense. So go ahead and give that a try, and we'll see you tomorrow in class. Thanks for watching.